Hello everyone, today we're talking about our case study POI-based assessment in disaster contexts. This course focuses on the application of spatial analysis methods in disaster contexts, with a specific emphasis on POI-based assessment. After a major disaster, cities face immediate challenges related to damaged infrastructure, disrupted services, and limited operational capacity. In such situations, rapid and reliable situational awareness is essential. Points of interest play a key role in post-disaster analysis because they represent functional urban services such as healthcare facilities, energy infrastructure, financial institutions, and governmental buildings. Evaluating damage at the POI level allows decision-makers to quickly understand which services are operational, which are impaired, and where critical gaps exist. In this course, a real-world case study from the 2023 Kahramanmaraş earthquakes is used to demonstrate how POI-based spatial analysis can support emergency response and recovery planning. The course shows how damage mapping, spatial integration, and category-based assessment can be transformed into actionable decision support for disaster management. In February 2023, the Kahramanmaraş region experienced two major earthquakes occurring on the same day. These high-magnitude seismic events caused widespread destruction across multiple provinces and affected millions of people. The case study focuses on the urban core of Kahramanmaraş, where dense settlement patterns and vulnerable building stock increased the severity of damage. Residential, commercial, and public buildings were heavily impacted, leading to large-scale urban disruption. Beyond physical destruction, the earthquakes caused significant damage to critical infrastructure and urban services. Healthcare facilities, transportation systems, energy networks, and governmental institutions were affected, highlighting the need for rapid and spatially informed assessment methods in disaster response. Critical infrastructure refers to the systems and services that are essential for the functioning of cities and societies. These include facilities and networks that support health, safety, security, and basic governance. When these systems fail, the impact of a disaster is significantly amplified. In urban contexts, critical infrastructure typically includes healthcare facilities, emergency services, energy and water networks, transportation systems, and governmental and financial institutions. Each of these components plays a vital role in both immediate response and long-term recovery. After a disaster, the functionality of critical infrastructure becomes a top priority. Emergency response, coordination between institutions, and the ability to deliver aid all depend on whether these systems remain operational. Understanding the spatial distribution and damage status of critical infrastructure is therefore essential for effective disaster management. POI-based assessment focuses on the functional elements of the city rather than only its physical structures. Points of interest represent services, facilities, and institutions that people rely on daily, such as hospitals, schools, energy facilities, and government buildings. For this reason, POI serve as effective indicators of urban functionality. Compared to building-only damage analysis, POI-based assessment offers significant advantages. While structural damage mapping shows where buildings are affected, it does not directly indicate whether essential services are available. POI-based analysis shifts the focus from physical loss to service disruption, which is more relevant for emergency decision-making. In post-disaster contexts, POI-based assessment enables rapid identification of which services are operational and which are not. This information supports the prioritization of emergency response, allocation of resources, and planning of recovery actions, making POI-based methods highly valuable in disaster management. The case study focuses on the urban core of Kahramanmaraş, specifically the 12 Şubat and Dulkadiroğlu districts. These areas represent the administrative, commercial, and service centers of the city and were among the most heavily affected during the earthquake sequence. The urban structure of the study area is characterized by dense residential development combined with mixed-use buildings that host public services, commercial activities, and institutional functions. This concentration of functions increased the exposure of critical services to seismic damage. Kahramanmaraş is located in a high seismic risk zone, and the building stock in the study area is heterogeneous in terms of age, construction quality, and structural resilience. These characteristics contributed to the observed spatial patterns of damage and service disruption following the disaster. Multiple spatial data sources were integrated to conduct the POI-based assessment in this case study. The primary spatial layers included detailed building footprint polygons and administrative boundaries defining the study area. POI data was collected through field surveys and focused specifically on critical infrastructure and essential urban services. This dataset provided information on the location and category of services such as healthcare, governance, energy, and transportation facilities. In addition to POI data, official post-earthquake building damage assessments were used to classify structural damage levels. Satellite imagery and orthophotos supported validation and spatial accuracy, enabling a comprehensive integration of GIS and remote sensing data for post-disaster analysis. To support effective disaster analysis, POI were classified with a specific focus on critical infrastructure. The primary goal of this classification was to highlight services that are essential for emergency response, coordination, and recovery, while reducing analytical complexity. Detailed POI types were aggregated into broader critical infrastructure categories. This approach allowed the analysis to focus on functional importance rather than excessive categorical detail, making results easier to interpret for decision-makers. Examples of critical POI categories include healthcare facilities, energy and utility services, governmental and public administration buildings, and financial or communication services. This classification framework enabled systematic evaluation of service disruption and infrastructure resilience following the earthquake. Building damage classification is a fundamental component of post-disaster analysis. In this case study, official damage categories defined by governmental authorities were used, including collapsed, severely damaged, and moderately damaged buildings. Damage severity matters because structural damage does not automatically translate into the same level of functional loss. A collapsed building represents complete service loss, while a severely damaged building may be partially usable or completely non-operational depending on the service type and safety conditions. In POI-based assessment, building damage categories are used to infer service functionality. By linking POI to the damage status of the buildings they are located in, analysts can identify which services are likely to be unavailable and prioritize interventions accordingly. The methodological framework of this case study is based on a GIS-driven spatial overlay approach. The core idea is to integrate POI data with building damage information in order to assess the functional impact of the disaster on critical infrastructure. The main analytical step involves performing a spatial join between POI and building polygons. This operation assigns building damage attributes to each POI based on its spatial location. As a result, each POI is tagged with a damage status that reflects the condition of the structure it occupies. Multiple data sources were integrated within this framework, including GIS layers, remote sensing products, and field survey data. Cross-checking between these sources was used to validate results and improve reliability, ensuring a robust post-disaster assessment. Identifying damaged critical infrastructure is a key outcome of the POI-based assessment. This process focuses on determining which POI are located within damaged buildings and categorizing them according to the severity of structural damage. The analysis is largely automated through GIS-based spatial operations, allowing rapid processing of large datasets. However, for highly critical facilities such as hospitals or emergency centers, manual validation is also applied to ensure accuracy and reliability. From an operational perspective, this approach enables fast identification of non-operational or at-risk services. By providing clear and spatially explicit information, the analysis directly supports emergency response planning and decision-making in the immediate aftermath of a disaster. Here it presents an overall overview of damage to critical infrastructure POI across the study area. The analysis summarizes the total number of critical POI identified in the city center and highlights how many of these were affected by building damage following the earthquake. Aggregated results provide a citywide perspective on service disruption. While individual building damage is important, understanding the proportion of affected critical services is essential for assessing the functional impact of the disaster. These results support strategic decision-making by offering rapid situational awareness. Emergency managers and planners can use this information to understand the scale of service loss and to prioritize response and recovery actions at the city level. Category-based damage analysis examines how different types of critical infrastructure were affected by the earthquake. Instead of focusing solely on total numbers, this approach evaluates damage patterns across infrastructure categories such as healthcare, energy, governance, and financial services. Some categories experienced higher damage ratios than others, reflecting differences in building stock, spatial distribution, and exposure. These differences have important functional implications, particularly for emergency response and coordination. It is important to interpret these results in terms of criticality rather than absolute numbers. Even a small number of damaged facilities can have a significant impact if those facilities play a key role in disaster response or recovery. Spatial analysis of damaged POI reveals clear clustering patterns across the study area. Damage to critical infrastructure is concentrated primarily in the dense urban core, where building density and service concentration are highest. In contrast, peripheral areas show a more dispersed pattern of damage. While fewer critical POI are located in these areas, their loss can still have significant implications due to limited service alternatives. These spatial insights help identify high-risk urban zones and support location-specific intervention strategies. Understanding where service disruptions are concentrated allows decision-makers to target response and recovery efforts more effectively. The spatial identification of damaged critical infrastructure has direct implications for emergency response. One of the primary benefits of POI-based analysis is the ability to distinguish between usable and non-usable facilities shortly after a disaster. This information supports response prioritization by guiding the allocation of emergency resources and helping identify alternative service locations when primary facilities are damaged. For example, healthcare services can be redirected to operational facilities based on spatial availability. In time-critical disaster scenarios, reducing uncertainty is essential. POI-based spatial analysis provides clear, actionable insights that support rapid decision-making during the early phases of emergency response. Damage to governmental and public administration buildings poses significant risks to disaster coordination and response. These institutions play a central role in organizing emergency actions, distributing resources, and communicating with the public. When governmental facilities are damaged, operational continuity is disrupted. This can lead to delays in decision-making, reduced coordination capacity, and increased uncertainty during critical response phases. The case study highlights the importance of resilient public facilities and spatial redundancy. Ensuring that governance functions are not concentrated in a single location is a key lesson for improving institutional resilience in disaster-prone cities. The sectoral analysis highlights how damage affects different types of critical infrastructure in distinct ways. Healthcare facilities are particularly sensitive, as their functionality directly influences survival rates and emergency medical capacity after a disaster. Energy and utility services represent another critical sector. Damage to energy distribution facilities can trigger cascading effects, disrupting communication, healthcare, and other essential services. These interdependencies increase overall system vulnerability. Financial and communication services play a key role in recovery and continuity. Damage to these facilities can slow economic recovery and hinder coordination efforts, emphasizing the need for sector-specific resilience planning. The value of POI-based assessment lies in its ability to transform damage mapping into actionable decision support. Rather than producing static maps, the analysis generates information that directly informs operational and strategic decisions. In the short term, outputs support emergency response and logistics by identifying which facilities are operational and where alternative services are needed. In the long term, the same data supports recovery and reconstruction planning by highlighting systemic vulnerabilities. Integrating these outputs into disaster management workflows enhances coordination among institutions and improves the overall effectiveness of response and recovery efforts. The POI-based approach offers several strengths in disaster assessment. It enables rapid evaluation of service functionality and shifts the focus from structural damage to functional impact, which is more relevant for emergency decision-making. However, the approach also has limitations. Results depend heavily on data quality and completeness, and the assumption that building damage directly corresponds to service loss may not always hold true. Some services may remain operational despite structural damage. Despite these limitations, the approach is highly transferable to other disaster contexts and cities. With appropriate local adaptation and data validation, POI-based assessment can support disaster management in a wide range of settings. Beyond immediate response, POI-based disaster assessment contributes to long-term urban resilience planning. By identifying vulnerable service networks, the analysis provides evidence for targeted resilience strategies. Integrating disaster insights into urban planning helps cities move from reactive response to proactive risk reduction. This includes strengthening critical infrastructure, improving spatial redundancy, and reducing exposure in high-risk areas. From a policy perspective, the case study supports informed investment decisions and helps prioritize actions that enhance the resilience of critical urban systems. This case study demonstrates the value of POI-based assessment in understanding the functional impact of disasters on cities. By integrating spatial data and focusing on critical infrastructure, the approach provides actionable insights for emergency response and recovery. Learners gain an understanding of how spatial analysis methods can be applied in real-world disaster contexts. The course emphasizes functional assessment, spatial thinking, and decision support-oriented analysis. Together with courses 431 and 432, this course completes the learning pathway from urban data foundations to analytical methods and finally to applied, real-world decision support in disaster management.